Hey guys, so today what we're going to do is we're going to do work and energy examples. And I'm going to show you guys just how they kind of work. Pun, I guess. So just how to do work problems and how to do energy problems and how to do conservation of energy problems. So here we go. Our first example is going to be this guy. Let me just make this bigger. Let's do 20. So we want to know um, a 75 kilogram firefighter, so it's giving us his mass, climbs the stairs, climbs the flight of stairs 28 meters high. And we want to know how much work is he going to do when he does that. Okay, so if you guys remember, the equation for work was force times distance, right? So what we need to do is we need to figure out the force that he's doing to propel himself upward and the distance that he goes. Okay, right? Because work equals force times distance, and then cosine of theta, where theta is the angle between them. So he's going to go 28 meters high. That will be our distance. So that's not an issue. But now we need to figure out the force, and then we need to figure out the angle between them. So if we're actually looking at this, right, it doesn't really tell us anything about this guy's climb, but we have a firefighter here, right? And you know, he's got his like helmet. Oh, this is a really bad helmet. Um, and he's basically climbing some flight of stairs, right? We don't know how the stairs look, but in general, he's going to be going upward, okay? And it doesn't matter the path taken, right? If you guys remember from the previous lecture. It doesn't matter how he climbs. So for the network done, it doesn't matter how he climbs. And it can be, you know, it can be this path, it can be like this path, or it could just be straight up. It doesn't really matter. It's the same work done each time because he's going against gravity, right? So he's going against gravity, and he's using the normal force to do it. So the normal force propels him up against gravity. Okay? So if we were to just do, you know, if we were to do the free body diagram of him, we have the normal force going up, and we have gravity pointing down. This is same direction as his displacement or distance, okay? Displacement in this case, but we've been treating it as distance, okay? So that means work here will equal force, normal force, times his distance, times cosine of the distance, or the angle between them, which is 0, which is just 1. So the work equals the normal force times the distance. So now, what is the normal force going to be? Well, the normal force is going to be Fn will equal F of g, right? Because if we look back at this, Fn minus Fg, right? And we usually approximate this as 0 because he's moving constantly. Remember, constant velocity means 0 acceleration. So you're not explicitly told that he's not accelerating, but they don't give you any information about his acceleration. So typically with these types of problems, there's none here. So Fn, so the normal force equals gravity, the force of gravity, which equals mass times gravity. So the work done equals mass times gravity equals the distance. So, and we're given all of that information. So 75 kilograms, 9.8 meters per second squared, and 28 meters, which ends up being 2.06 times 10 to the minus 4 joules. Typically when we're dealing with work and energy, these numbers will be kind of big. Okay, so that's number one. Let's look at the next example here. And this is also going to be about work. Okay. I did 20 last time, right? So there's a lot here. Let's do this. Okay. Let's separate it like that. So, what is the work required to push a lawnmower 25 meters if the worker is pushing with a constant 75 newtons on the handle of the lawnmower at an angle 35 degrees below the horizontal? And then we want to know, so that's step one. So we need to know what is the work required to do that. And then we want to know how much work does the normal force do on the lawnmower during 25 meters of pushing. And then we want to know if we add a frictional force to the ground of 20 newtons, how much work does that do on the lawnmower during the 25 meters of pushing. So if we draw a free body diagram right here, and we say, okay, we're pushing it 25 meters with a constant 75 newtons. So, and it says 35 degrees below the horizontal. So our free body will look like this. So this is 35 degrees. And notice this, the force of the push here, 75 newtons, it will not be in the direction of the displacement, right? Because you're pushing a lawnmower, and it's going to be moving, you have a lawnmower, right, from the side on some grass. This is a pretty poor little lawnmower here. Maybe if I had the little thing on top. And it's going to be going this way while you're pushing this way, right? So the angle between these two will be 35 degrees. So work will be FD cosine theta, 75 newtons, 25 meters, cosine 35 degrees. Okay. And when you do the math on this, this ends up being 1.54 times 10 to the 3 joules. And again, a joule is a Newton meter. Okay. So that's the first question. Now we want to know, how much force does the normal force do on the lawnmower during this? Well, so normal force then. So the work of the normal force, again, equals FD cosine theta. And if you look at the free body of this situation, so again, we have the push. But we've also got the normal force, right? And if we're being complete, we have gravity. And so we've got this, right here where it's going in this direction. But the angle right here is actually 90 degrees. And so if we do, Fn, right? D cosine of 90 degrees. We don't know what the normal force is yet. It would be mass times gravity, just like before, because they're going to be equal. But this guy is 0, right? Cosine of 90 degrees is 0, because the normal force and the direction it's moving are in different directions. So the normal force actually doesn't do any work here. No work done on the lawnmower by Fn during push. Now, as we're doing work, notice I've been using the word on. So we're talking about work on the lawnmower. remember that when we're talking about work, we can do work on an object, and that pushes, that gives that object energy, right? But it can also, work can also be done against the object, which would take energy or work away from the object, right? So gravity for the firefighter, right? The normal force was putting work into the object, but gravity was taking it away. It's just they were doing it at the, we were just talking about the normal force in that one and not gravity, right? So, where am I at? Right. We need to do the next part. Okay, so we did this normal force. How much work does it do on the lawnmower? Nothing. So now let's talk about the frictional force. Okay, so if we add a frictional force to the ground to 20 newtons, how much work does that do? Okay. Oops. So we got a frictional force here. So force of friction. So friction points in the opposite direction, if you remember, right? It is opposite to the motion, and the motion is to the right. It would point to the left. Okay. So our complete free body diagram in this instance would look like this. Okay. So these guys, the direction of the displacement, which is to the right, and the force of friction point in completely opposite directions. So the work of friction would then be force of friction times d times cosine theta. They tell us this guy's 20 newtons. This guy was 28, or wait, 25, 25. 28 was the previous one. And then cosine of 180 degrees. And this guy is -1, right? So we're going to get negative work here. And this is kind of what I was talking about. Work done on an object can be positive or negative as well, right? And so we multiply those two numbers together, and what do we get? We get -500. Right? It subtracts energy away from the system. Okay? So there's just a couple examples of how to do work calculations. Okay? So pay attention to direction. Pay attention to if it's on or against, right? That will tell you the direction of the force acting. And then you'll know, is the work going to be positive or negative on the object? Okay. So let's do the next one. Now we're going to move into basically energy calculations. And then we'll start to do conservation of energy. Okay? Type of question. So a 10-kilogram ball is 15 meters high. And you want to know, what is the velocity on the ball just before it hits the ground? Okay. So if you remember the last lecture, there are two types of energy that we're really concerned with. There's potential energy, and then there's kinetic energy, right? And they're related through energy conservation. So how you do these types of problems is you kind of want to set up energy initial and energy final. So you want to set up two energy states, and then you're going to want to set them equal. Okay? So it tells us a 10-kilogram ball is 15 meters high. So you want to set this up. Okay? And so height is 15 meters. Okay. And then our final, what we'll see is you want to do it the instant before the ball hits the ground. Okay, so this is the E final will be instant And the reason you do this is kind of like when you're doing kinematics in general, is you don't want to talk about motion after it's already completed, because that won't give you a sense of what's going on. You need to talk about it during the process of motion. Otherwise, you're not going to get a sense of, like, you're not going to be able to model it correctly, basically, using what we currently do. So we always do the instant before, and the reason you do that is down here, this will have a negligible height. Okay, so we won't have to worry about potential energy up there. Okay, so we've got energy initial here. Energy initial, and then we've got energy final. Okay, so energy initial. What you do is you look for the 3 types of energy that we talked about. Well, 2 types, but one splits into 2 types. So you have potential energy, which can either be gravitational potential energy or spring potential energy. There's no springs in this problem, so you don't need to worry about that. And the other type of energy you need to worry about is kinetic energy. Is the object moving? So in the initial state, all we have is you've got it's lifted above the ground, okay? And so what we do here is we mark the ground as our 0 point, okay? So gravitational potential energy is a potential energy that exists if you're not at that 0 point. If you're above what you define as the 0 point, okay, so you have to define it just like you do in other, in kinematics, you have to define the ground as 0, or you have to define a starting point, right? So since it's above that, it would have positive gravitational potential and energy. If you move the ball beneath the 0 point, you would have negative gravitational potential energy. Okay, the ball in the initial energy state isn't moving. So you would write, it's only got, here, let's do this actually, gravitational potential energy. Okay, and so EI here is equal to just mgh. It's the mass, because it's the force of gravity times the distance, right? It's the work equation, repurposed. In the final state, so there's still no springs, so we don't have to worry about that. And it's negligibly above the ground, so there's not really any gravitational potential either. But it is moving, so it has kinetic energy. So E final, and remember we derived this from using kinematics, okay, as well as the work equation. So now we set them equal. And we can solve. GH equals 1/2 v squared. We wanted to solve here, I think, for velocity. So we're going to multiply the 2 over and take the square root. Take the square root. And now you can solve mathematically. 10. No, 15 I do. And if you do the math on that, you get 17.15. If you're actually curious, we solve this type of problem of a ball falling, given this information, with kinematics. And if you solve it with kinematics, you get the same answer. Okay, so you can solve this with kinematics as well, using well, we don't know anything about time, but you could use probably the V final equation with position, and it would give you the same equation. So here's my go-to on how to solve for energy conservation. So how to solve energy conservation problems. And this is kind of what we did in this problem right here. So step 1, define energies throughout the problem and a 0 point. Okay, so what we did here, we defined our 2 energies in this case. You can have more. Maybe there's multiple things going on. Like you'll see with the spring problem later on, there's multiple energies. But here we only had an initial and a final. So you define multiple energies throughout the problem and you define your 0 point so that you can define your gravitational potential energy. So kind of like, I guess 1A here would be look for GPE, gravitational potential, SPE, spring potential, and kinetic energy. Okay. Step 2, set equal or set energies equal and solve. Okay. Which is what we did. So that's kind of it. And every single problem will work this way. Okay. The main thing is you have to be careful on some of these. And as you'll see, it can get a little bit hectic. Okay. With springs, it can get kind of hectic. But I'll show you how to do it. Okay. You don't have to worry about vectors or anything else when you're solving with energies. And again, a lot of these problems you can also solve with kinematics, okay, if that's your preference. But energies are fairly easy, okay, relative to forces, relative to kinematics. I personally think they're easier. And so if I can solve a problem with energy, I usually do, just because it's easier to do. So the frictionless roller coaster system shown below, so let's go ahead and draw this. So, shown below has different velocities at different points throughout the track. Find the velocities at those different points, given the heights in the picture. So here, because I'm still drawing the problem for you, I'm just going to draw all the heights. And normally with these types of problems, you'll be given the picture. And so the picture in this case is going to look like this, where y1, so the first height is 20 meters high, y2 is 10 meters high, y3 is 15 meters high, and y4 is 5 meters. Find the velocities at different points given the heights in the picture and the fact that the coaster starts at 0 meters per second at y1. Okay? So it actually isn't moving initially. It just kind of drops and then it starts moving. Okay, so it's a non-powered coaster. I could do a powered problem and just say, oh, it's moving at this rate at this beginning, but I'm not going to. Not for this problem. So how we do this is we start off, we look at our list, we say define energies throughout the problem and a 0 point. My 0 point is going to be where these guys are already relative to. So I'm going to say right here is 0. So relative to this point at y1, E1 I'll call it, has mgy1. And it's not moving because not moving. Okay. You now have this this particular one, so E2, mgy2, and it does have, at E2, it will have a kinetic energy. Because at this point, if it's dropping, I forgot to actually draw the actual coaster. There you go. If it's moving down, it will, or if it's dropping here, it will have a velocity by the time it gets here, here, and here. It will have a velocity beneath 20 meters. If it's 20 meters high again, it will not, because it's using all of its energy to be that high, right? Because this is the only energy in the system. So E2 will have a kinetic energy. We'll just call it KE2. E3, mgy3 plus KE3. And then Y4, K. So that's pretty much it. All of these all kind of look fairly similar. There's no springs in this problem, so we don't need to worry about that. But these would be our energies at each point. They have a potential energy because they're all not at zero, positive potential. And I forgot to draw this down further. And they all have kinetic energies except for this guy because they're moving. Okay. So we want to solve for the velocities at the different points. So we need V2, V3, V4. And they're embedded in these kinetic energies. So the easiest way to do this, set energies equal and solve. E1 equals E2 equals E3 equals E4. And so what we're looking at then is you can do this however you want. You can do E1 equal E2, E1 equal E3, E1 equal E4. You can do E2 and E3, E3 and E4. I think it's easiest to compare everything to E1 because this only has one term in it, mgy, where these have mgy2 and kinetic energies. So I'm just going to do E1 equals E2 for the first one and solving for V2. But because all the energies are equal because of energy conservation, we can do it however we want. I'm going to write this out now. The masses will all cancel, which usually happens with these types of problems. The only way they're not going to cancel is when we have springs, because the spring potential energy isn't a function of mass. And remember, we want to solve for this guy. So because of that, I'm going to subtract over this over here. I'm going to multiply over the 2. Take the square root. And now we can plug in and solve. Here, let me pull out the g. G's in both terms, I can do that. Y1 was 20. Y2 was 10. And that ended up being 14 meters per second. So now we need to do the second one, or the third velocity and the fourth velocity. So I'm going to do the same thing I did basically. All of this will look the same. It's easier to compare E1 to E3 than E3 to E2 because you have so many more terms right here. So I'm just going to do the same thing. MGY3 can cancel the masses, subtract it over, multiply by 2, and we'll get the same thing here. You plug in the new numbers though, and you get 9.9 meters per second. And then you solve for V4 the same way. The difficulty in these problems comes from determining the energies in the different states. So at energy 1, what is it? What energies are present there? Energy 2, energy 3. That's where the difficulty lies. The math, I mean, it's no more strenuous than working with kinematics. And of course, really, the only thing that changes here is V4 the whole time. So the formula ends up looking the same. But just to be super obvious here, notice the lower you go, right? So V4 is the highest, 17.15 meters per second. And it's the highest because it's at the lowest height. So the coaster, all of its energy, because we didn't give it an engine, because we didn't give it a motor, all of its energy that's in the entire system starts with gravitational potential energy. And as you use or convert gravitational potential energy into kinetic energy, that kinetic energy goes higher. So you'll notice that Y4 is the highest because it has the least height. So there's the least amount of energy in gravitational potential energy and more in kinetic energy because of that. That means Y3, which is the highest relative to Y1, has the smallest velocity. Okay? So as you convert gravitational potential energy into kinetic energy, you'll see that your gravitational potential energy goes down and your kinetic energy goes up. And it can just go basically back and forth. Okay? So you're not losing energy because of because of energy conservation. So this next problem does use a spring because I want to show you guys how springs work. Okay, how spring potential works. You use a spring launcher, and this problem is decently complicated, so let's spend some time on it. You use a spring launcher to launch a 10-kilogram ball into the air. The launcher points straight up, and you push the ball 0.1 meter into the spring to initiate the launch. If the spring constant is K equals 100 Newton per meter for the spring, how high does it go? Remember that the spring constant is the stiffness of the spring. So you can imagine if a spring is stiffer, it's tougher, that spring constant would be higher, and then the ball would be able to fly like really, really high, right? So we want to know if the spring constant is that, how high does it go? And we want to know how fast was the ball going just after the spring finishes expanding. So what we need to do first is we need to draw the system, okay? Because we need to identify the energies. So step 1 is, identify the energies. Okay. So you're using it to launch a ball into the air. So what I'm going to do is I'm going to go ahead. I'm going to draw this. This is my 0 point. And I'm going to draw my spring uncompressed. So this is before anything has happened. And I'm going to say this is 1, and I'm going to say no energy yet. This is before anything happens. And the main reason I'm writing this down, so you have the ball on the spring but you haven't compressed it, is because I want to set the 0 point here where the spring isn't compressed. Next, you're going to push into the spring. Okay? And so now we have some displacement here because you push the spring down. And we'll call this distance y spring. So E2, you will have spring potential energy because the spring, but you will also have negative grav potential. So negative GPE. And it's negative because you are going beneath, you're going lower than y equals 0. Okay, you're going not above it, you're going below it. Okay, so if you set that 0 point and you're not at the 0 point, you have gravitational potential. If you're above it, you have positive. If you're below it, you have negative gravitational potential. And I'll show you how that works. At the next point, the ball releases. Okay, so this spring, so you compress it and then you release it. And the ball is now flying up into the air. Let's set it right here, just after it releases. And it's now got v. Okay, so it's now moving at a velocity v, or about to. And here, if we set this the instant above y equals 0, we can say this just has kinetic energy. So the ball is just released. Okay? Here was compressed. And then I'm running out of room, so I don't want to like okay. So here you'll only have kinetic energy. You're not going to have gravitational potential energy because it's the instant after. And you're not going to have any spring potential because it's now separated from the spring, if only by a minute distance. The next one is the ball up in the air. Okay, so this is after the ball's been compressed, and now it's flying high in the air, or it's in the air. And we're going to say this is y max. And what happens at y max? V equals 0. So this is ball at highest point. Okay. So this is when the ball is at its highest point, v equals 0. Okay, because we want to know how high does it go. And we also want to know how fast was it going right after the spring finishes expanding. Okay, and we'll call this guy E4. And this will only have gravitational potential energy. Okay, so now let's go ahead and mark out mathematically what our energies are. So E1, again, 0. This is before anything happens. E2, we're going to have spring potential energy and negative gravitational. So E2 will have 1/2 K, and then the displacement squared. So y spring squared. and then it will be minus our gravitational potential energy, minus mg y spring, okay? Because y spring is our distance here. That's what I called it. Next up, we have E3. E3 is the kinetic energy. So E3 is actually pretty easy to get. So E3 will be just 1/2 mv squared, where m's the mass of the ball. E4 is just gravitational potential energy. So that will be mg y max. Okay. And so these are our points, and we need to solve for two things here. We need to solve for v and y max. So we need v, the point after it was just released, and the highest point it reaches. So we're given k. We're given how much it's compressed. I believe we can solve this by just setting E2 E2 and E3 equal. To solve for V. And then when we have that, we can set E3 and E4 equal, and that will make that really easy to solve for Y max. So, E2, we just wrote it, 1/2 k y spring squared. So, minus mg y spring, that's E2. E3 is 1/2 mv squared. We need to solve for this. So what we can do here is multiply the whole thing by 2, multiply this 2 across. Divide by m and take the square root. So there is a lot to write here. And if you plug this in, y spring was 0.1 squared minus 2. I believe the mass was 10 kilograms. Yeah. Y spring again, 0.1 over 10. And if you plug in all those numbers, you do the math on that, you get that V is equal to 9.9. And yeah, that's the velocity. Okay, so now what we can do is we can set E3 and E4 for Y max. So now we have E3 equals E4, and so you have 1/2 mv squared, just kinetic energy, right? Because this is when it's leaving. And then this is mgh. And so this is easy for us. You just need to solve for h, right? Or, sorry, this was Y max, huh? Divide by g. And if you remember, v squared over 2g, that's what you also get if you do kinematics. One of the meters will cancel. And then the second squared will cancel with that second squared, and so you're left with units of meters. And this gives you 5 meters. Okay, great. So again, the hardest thing here is setting up this, identifying the energies. And it can be challenging, especially when you're compressing the spring, and you're compressing the spring and you think, oh, I only have spring potential there. But it's not true because you're away from the 0 point, so you also have negative gravitational potential energy. I think this is where you'll have your greatest challenge, is remembering to have gravitational potential energy at points like that. Okay. Next problem. A 10 kilogram skier, that's not really, that is not, if someone's 10 kilograms, they're not very big. A 10 kilogram skier is skiing on a slope with 0 friction, and they want to know their speed at the bottom of the slope. If they know that the angle of the slope was 30 degrees and the distance they traveled down the slope was 10, what is their speed at the bottom? And then it says if there's a frictional force added, what is their speed now? So, how this type of problem works. You have a slope, kind of looks like, you know, like some cheese or cake or something. And you got a skier on top. I've done skiing problems before, right? I usually give them like a little hat, right? It's pretty funny. So you got a skier going there, and we know that his height. Oh, we don't know his height. Okay, so he's got some height. We don't know what it is, but we do know he travels down the slope. Whoops. Let's do this better. Let's do this guy, green. So he travels down the slope, and this is 10 meters. Okay. And we've got an angle of 30 degrees. Okay. So we want to know what's their speed at the bottom. So we do the same thing we did before. Let's set 2 energy points. So we'll call this E1, this E2, or energy initial, energy final. Doesn't matter. So E1, he will only have, if we set this as our 0 point, he's only going to have gravitational potential energy. Okay? It doesn't tell us they're moving. I'll just be more explicit with it. The skier is released from rest. Okay? They'll be explicit if they're moving beforehand. So they only have gravitational potential energy. So that means mgh, right? E2 at the bottom, they're at the bottom, there's a 0 point, 1/2 mv squared. They won't have spring potential because there's no springs or anything like that. So this problem then reduces to E1 equals E2, right? But there's an issue. We don't know the height. So there's a little wrench in our plans, right? They threw a wrench in our plans. We don't know height. But we do know two things that can help us get it. The angle and the distance that he travels. So if you notice angle, distance, opposite side, this is forming a triangle for us, right? So if we can do sine, right? So sine is opposite over hypotenuse. So we find height. Sine of 30 degrees equals the opposite, which is h, over the amount traveled, which is 10 meters. So h equals 10 sine 30 degrees. And so this gives us 5 meters, because this is 1/2. Great. Now we can actually solve. So mgh equals 1/2 mv squared. We're solving for v. What was their speed at the bottom? So 2gh, and v equals the square root of 2gh. 2, 9.8, poorly drawn, and then 5. And once you do that, you are left with, again, 9.9 meters per second, because I like to use, I guess, the same numbers for everything. Okay. Now we need to do the second part. If a frictional force of 20 newtons is added to the skis, what is the speed now? Okay. So, with friction, how you do it is your equation is EI minus non-conservative work equals E final. So EI minus the work of friction equals EF. So EI, or E1, I don't know, I'm using I guess, but I was using E1, E2, minus force of friction times distance times cosine of the angle, although we already did. You don't have to actually worry about that because that's built into this negative sign here. That's where the negative sign comes from. I guess you could do plus, 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 and then cosine of that. And then this becomes -1 because cosine of 180. And so then you get E1 minus force of friction D equals EF. Okay, so now we can actually start doing this. So now we do mgh minus force of friction, which they told us was 20 newtons, times the distance, which they said was 10 meters. And then, because they said, right, so force of friction, where's my drawing? He's going 10 meters. And frictional force is 20 newtons, right? And so EF is your 1/2 mv squared. Okay. So now we set up the same problem solving for V. 10 kilograms, 9.8, height is 5. This is minus 200 Newton meter or joules. And then we just need to multiply by 2, divide by 10, and take the square root. And when you do the math on that, I got 7.6. So, notice that the velocity is slightly less than it was before, and that's because we added a frictional force. That's to be expected. Okay. We've got 2 more problems to go. Okay. 2 railroad cars, each of mass 66,000 kilograms, are traveling at 23.6 meters per second toward each other. They collide head-on and come to rest. And we want to know how much thermal energy is produced in this collision. So, if we draw this, this is a very different problem than what we're used to. But if we go ahead and draw this, we got 23.6, 23.6, and they're going to come towards together. So this is E1. And then E2, they're going to collide and release thermal energy. After colliding. So this E1 here is just kinetic energies. So the sum of KE. Because they're moving together and they'll both have it. E2 is all what I'll just call thermal energy. So thermal energy. Because the railroad cars are going to stop. They're going to be, they're going to collide with each other. They're not going to be moving anymore. There's no more kinetic energy. What we're being told is that all of that energy is being converted into thermal energy. Okay? So, what we end up doing then is we've got EI, right, plus non-conservative work equals E final. Okay? So, this, there's 2 ways you can do this. You can assume that E final is 0 and that the non-conservative work is being subtracted, which ends up moving that over. Or you can assume that this is 0 and that E final is only thermal energy. Either way, you end up with E1 equals E2, and you get KE1 plus KE2 for the 2 cars equals thermal energy. Either way, this is what you end up with. So you get 1/2 mv squared plus 1/2 mv squared equals thermal energy. And they have the same mass and the same velocity, so these add together. And so all we need to do is basically multiply and solve. So 66,000 kilograms, right? Times 23.6 meters per second. That's squared. So this is 3.7 times 10 to the 7 joules of energy released. Okay? And you'll be told if energy is, basically you're going to be told in a problem if energy is not going to go towards something. So for example, if they said it's losing energy to friction or something like that, it will tell you where the energy is going. Okay? Our final problem is kind of a longer one, I believe. Maybe I'm wrong on this. We will see. But it's a trampoline artist. And they're jumping upward from the top of a platform. Oh, I changed this problem a bit. Okay. So a 62 kilogram trampoline artist is jumping upward from the top of a platform with a vertical speed of 4.5 meters per second. And we want to know, how fast is he going as he lands on the trampoline 2 meters below? Okay. So, how this looks. Okay. So this is his initial starting point, right? He's going to jump up, and then he's going to come back down. I'm going to call this y equals 0 down here. Whoops, let's do this. And this is going to be his E final position. So at E initial, he's starting here. He's jumping up. He's going to jump up with some velocity v, right? But then there's going to be parabolic motion, and he's going to fall down back to this point. And he's going to have this same velocity, okay, between these 2 points, right? If you remember when we threw the ball up with when we were solving for kinematics and we were throwing a ball up and down, it's symmetric motion. And so when we jump up with v, we are also moving back that same point with v. So EI then equals that same kinetic energy plus we'll have some gravitational potential energy, where this will be H. Okay, and then when he comes down here, let's call that KE initial. Down here, he's going to hit the 0 point. We're going to say E final equals KE final. Okay, because these will not be the same kinetic energies. We want to know that final speed. So we just set these guys equal to each other. The hardest thing about this problem when you're figuring out initial energies is figuring out that he's jumping up, but then he's coming back down. And so figuring out that initial kinetic energy is the trick here. And of course, he will have the potential energy as well. So 1/2 m vi squared is what I'll call it, v initial squared, plus mgh. E final will just be 1/2 m v final squared. And we just want to solve for this. So we're going to do 1/2 m, or let's do where I say, you know, E initial equals E final. Now what I'm going to do here is I don't really like these 1/2, so, well, actually when we multiply by 2, we'll get rid of them. Okay, that works. So we're just going to cross off the m's, because they're all the same mass in the problem. And then we're going to multiply this 2 over. Same thing as multiplying the whole equation by 2. And then we take the square root. This was our initial velocity, which was 4.5 meters per second. We're going to square that guy, plus 2, 9.8, and my initial height, 2 meters. So that ends up equaling, you do the math on that, 7.7 meters per second. So yeah, that's basically energy. That's energy conservation and stuff like that. There's not really much more that you'll see in terms of problems from me. You can do a whole lot with energy. You know, like I said here, you got a small taste of it with the thermal energy. But you can do a lot with it. You just have to be given the types of energies that you're given, right? So what we'll mostly deal with, again, gravitational potential energy, spring potential energy, and kinetic energy, and the conversion between them. But you can also add other types of energy, like thermal energy. You just have to be told what it is, or the form that it takes. So thanks for watching, and I'll see you in the next one.